Okay, so 61C actually was in the news this week. Unfortunately, it wasn't particularly happy news, but thought you might find it interesting. The same week, I guess, we lost Steve Jobs, we also lost Dennis Ritchie, who you might recognize that name. He's the R in the K&R textbook that you're reading on. He was one of the inventors of the C language. Also one of the inventors of Unix, along with a fellow Berkeley EECS alum, Ken Thompson. And there was a really nice article about it in the New York Times. I recommend you take a look at it since it's relevant to what you guys have been doing. Since you're familiar with his work now, you understand sort of the premium he put on simplicity and elegance. One thing I thought was really kind of insightful in this article, more insightful than I'd normally expect in sort of a mainstream place like New York Times, was this recognition that when Ritchie and Thompson were working together, it was sort of the two places where computer science originally came from, right? You know, years ago in the 60s, there really wasn't a computer science. In fact, I'm not sure it was even EECS. It was probably just an EE bachelor's degree that Ken Thompson got in the 60s. And, you know, you either, if you're doing computer science, you either came from the math department or the engineering department. And what was interesting about these two guys is each came, you know, Ritchie came from math and Thompson came from engineering. And in some sense, you know, the elegance of both C and Unix, I think, comes from the fact that he had both kind of the more theoretical point of view and the more engineering point of view. So take a look at that when you get a chance. Brian was going to make an announcement about Project 2, I believe, in terms of, what did we decide you were going to announce before we get started? It wasn't accounts, it was the two phases, I thought, or I forget what we said. Oh.
If you haven't picked up your account form yet, I'd just like to announce that that's very important because that's how we're assigning grades for Project 2. So
Great. So, all right, let's get into the lecture. So, continuing the discussion on thread-level parallelism, here's where we ended up last week, or sorry, last class. Multiprocessor. This is on a single chip. Every processor has a local cache. There's an interconnection network. They all share the memory, right? So they all use the same memory. This is called a shared memory multiprocessor. Okay. Three things you might want to know about a shared memory multiprocessor. One is how do they share data. Two is how do they coordinate the sharing. And then three is sort of how big does it scale. Okay, so we talked about all that last time. So answer one was the way they're going to share memory is by sharing memory. So it's a single memory that gets used across all the cores. Okay, so all these different processors are using the same address space. The way they're going to communicate to each other, if you have a thread running on one core that needs to talk to another thread that's running on a different core, or even on the same core, the way they're going to talk is through memory, right? Because they share the memory. If two threads have a variable in that memory that they agree they're going to communicate through, then that's how they can talk to each other, right? Thread one does, puts a value in that variable. Thread two can read it, and so on. Okay, so that's how they're going to coordinate. So that's two out of the three questions, and we talked about the first one. We talked a little bit about the second one last time. I'm going to talk about it some more now. Okay. Number three is about scalability. We'll get there as well. Okay. So I showed you this last time, but I went fast, so I want to look at it again. Okay. So here's an example of how to use MIMD processing with multiple cores and multiple threads to solve a bigger problem. So let's say you wanted to take the sum of 100,000 numbers. Let's say you had 100 processors. Then what you would do is you distribute those 100,000 numbers across your processors. Each processor would add up its 1,000 numbers, and then you'd have to combine it. Then you'd add all those subtotals together to get the final total. Okay, so it's a divide and conquer. So phase 1, everybody adds up 1,000 numbers. Phase 2, you combine those. Okay, so we talked about this last time. All right, and then we looked at some code to do that. Okay, and remember what's happening is we have multiple cores, and we're going to run this code simultaneously on all the cores, and when they reference memory, they're going to be referencing the same memory address, right? So I asked you to think about how that's really going to work, okay? And I'm sure you're all excited about this, but we're going to have a clicker question about this in a second. And the clicker, yes, I see the excitement back there. And the question's going to be sort of how do you make this work? But let me remind you what the code looks like. So you start off saying you got 100 processors. That's the initialization. And then we're going to reduce the number of processors we're dealing with until we get down to 1, right? Because when you get down to 1, you've got the final answer. So we're going to repeat until this variable that's kind of not really very well named, but I couldn't think of a better name, gets down to 1. So you start with 100, it's going to get down to 1. So what are we going to do in that loop? We saw this last time. Well, first we're going to have a synchronization point. So synchronization just says, okay, nobody moves until everybody gets here. That's called a barrier synchronization. Okay, so the first thing you do when you enter this loop as one of the 100 processors is you wait until this call returns. That means everybody's there, then you can go. All right, so that's kind of a very heavyweight way of synchronizing things. We'll look at some cheaper ways later, but this makes sure that everyone is at that point at the same time. We're going to see why that's important in a second. All right, the first thing we do is we check for this weird corner case, which says, if we've got an odd number of processors, we're going to take the very last one. So we're going to divide by 2. We're going to take the bottom half of the processors, and we're going to say, okay, you're responsible for adding up your current sum plus the sum of your partner in the top half, right? So if you're the second processor in the bottom half, you're going to add up your sum plus the sum of the second processor in the top half. Okay? And so there's this weird case that if you have an odd number of processors, there might be one left over. So if there is, we arbitrarily decide, okay, if there's one left over, we're going to first add that to the sum at processor 0. So processor 0 is responsible for handling not only its stuff and its buddy's stuff, but also if there's an extra processor. Okay, now here's where the action starts. So we have this variable half that says how many processors we had when we started. We're going to say, okay, divide that by 2. So if we started with 100, we now have 50. Okay? We update half. And then we basically say, remember, this is running on all the processors. So this says, if my processor number, right, so I'm Pn, if my processor number is less than half, then take my sum. Okay, so this array sum is an array of all the partial sums for each of the processors. So I'm going to take my current partial sum, and I'm going to add to that the sum of my partner who's half the distance away. So again, if I'm the second processor in the first half, I'm going to add my sum plus the sum of the second processor in the second half, in the big half, in the top half. Okay? And then I iterate. Okay? Synchronize, and then go and do the next one. All right, so this is going to go, 100, 50, 25. Oh, that's odd. We're going to do something special. 12, 6. You can go from there, right? So what does that look like in animation? We're not going to do it with 100 processors because we'd all go blind. We're going to do it with 10. So we'll start with 10. So let's say you had 10 instead of 100. Okay. We've got partial. We have this array of 10 partial sums. All right. So in the first phase, everybody computes their own local sum. They have 1,000 numbers. They add them up. That's easy to do. All right. And then we start the next phase. So half of 10 is 5. So basically, the top half send their sum to the, well, they don't really send it, but it looks like that in this picture. But P0 is responsible for adding up its sum plus P5. P1 is responsible for its sum plus P6, and so on. Okay, and you just add those up. You saw the code for doing that. Great. Go to the next iteration. All right, well, 5 is odd, so we're going to have to do something with this odd processor out. So we're going to have P0 add up its partial sum with the odd guy. Then we do the rest of the algorithm. So now we're down to 2. 2 is even, thank goodness. So we just divide that in half. We get 1. P0 adds up those last 2, its and processor 1 sum, and you end up with the answer. Okay? Quick question. It's got to be quick. Yeah, so there's probably better ways to do this. So the question was, if you think about what's really happening here, right, we have that piece of code, and all the processors are executing that code every loop. So even though this picture kind of looks like after you've done your thing, you don't do any work, if you really look at the processing, all these processes are chugging away. It's just most of them, they're not less than half, and so they don't do anything. Okay, because remember, the place where you actually had to do an addition was only if your processor number is less than this value half. So you're absolutely right. You could come up with smarter ways to do this. Okay, good question. All right, so how is this going to work? All right, now this is where you guys got to pay attention, if you weren't already, because this is where the question's going to come up. So Dan's going to get ready with the magic question machine. Basically, shared memory as an abstraction isn't going to be enough to solve this problem, or maybe it is. That's one of the questions. Okay? But in general, to do this kind of computation, there's going to be cases where threads need to have a little private memory that they look at that nobody else looks at. Okay? So even if it's in the same address space, there's sort of a gentleman's agreement among threads that, this piece is for this thread, this piece is for this thread, this piece is for this thread. Everything else in memory, everybody can read it and write it. Okay? So in general, all threads have access to the same memory. If the data is going to be shared, then everybody can read it and write it. There's going to be some private data that we're going to agree can only be accessed by an individual thread. So if I have 100 threads, I've got 100 sort of individual private little pieces of data that that each of those threads can use. You as the programmer won't have to worry about this because there's going to be language support that actually gives you this abstraction of private versus shared data. So next class we're going to talk about one of those languages, which is an extension to C called OpenMP, and that'll give you the primitives for saying what's private and what's shared. Okay? But so does everyone understand there's data that everyone gets to look at, and then there's some data that's set aside for each individual thread. Quick question, are they all stored in the same place? They probably are, but you don't have to worry about it. Okay, but the language is going to make it look like they're not. Okay, they're going to have different addresses, if that's your... we only have one address space. So yeah. Okay. All right, good. So here's the clicker question. That's the same code. I haven't played any tricks. It's the exact same code. And then the question is, we've got three variables here. We've got half, which is this magic number that's telling us about the number of processors we're dealing with. We've got sum, which is an array, right, where we keep all our subtotals. And we have PN, which is the processor number. And the question for you guys is, for each of those, does it live in shared memory or private memory? And Dan has started the clicker thing. Yeah, let's go. Okay. And so you can see how it works out here. A is all private, E is all shared, and it goes in between there. Okay, let's see. Wow, this is fascinating. I wish you guys could see this. Do I have to tell them who's winning? Okay, we've got about 115, 16, 20, 26, 27. We should get up to a little over 200, according to my scientific experiment of how many papers seem to be left. All right, let's go a little more. We're at 170, so let's get a few more people to click in. Maybe we'll stop when we get up to around 200. Oh, it's getting slower, getting slower, getting slower. 180. All right, so what do we do now, Dan? Okay, we're going to stop at 180. Okay, so now talk amongst yourselves, and for a little bit, and then we're going to re-vote. Is that how we do it? Okay. Who's the winner? Oh, that's percentages. So 56. Ooh, this is a good question. You know the answer? All right, do we want to vote again, or how do you? In the interest of time, why don't we click in again? Wow. Okay, well, this will be interesting to see if you guys are right or I'm right. Okay, we're about halfway there. Let's get a few more answers. Keep clicking. All right. Okay, yeah, no, it's working here. We got 130. So 50 people decided they don't want to play anymore. Boy, results are almost the same as before. So maybe even, okay. All right, let's go a little more. All right, well, so D is the winner for you guys by far. So let's see if that's true. So D is the winner by 63%. C has 18%, and then the others are sort of, in the noise. Okay, so let's figure out the answer to this one because now I'm a little nervous. Okay, so PN. Does anyone have an argument for why that would be anything except private? I mean, PN is what's my processor number. If that ain't private, nothing is. Okay, so PN. If you got 100 processors, each one of those is going to have a private, a thread on that processor. Each one is going to have a private number that says, yeah, I'm thread 3. Someone else will have one that says I'm thread 7. That makes sense? Yeah. Okay, I didn't understand the question. Okay. Oh, okay. So the question is, if the processor numbers are private, how do the sums get distributed in the first phase? And I didn't show you that, but you could easily have an algorithm that just does that just takes the data and you take your portion for your processor number. So if your processor 0, you get the first percent. The processor 1, you get the second percent. But that has to be set up ahead of time. But it can still all happen independently. Okay? Yeah. Yeah. Okay, so I think the question is, how do I know how many processors I have available or threads available and set things up appropriately? And I'll show you that in a little bit. Okay? All right. So so PN has to be private because it's unique. It's different for every thread. Okay. What about sum, right? Remember, sum is an array, and so this might have been a little confusing. But sum is an array that has an entry for each subtotal. And remember, the way processor 0 adds, its subtotal plus its partner subtotal is it just looks in the array. It just indexes in the array. So basically, every processor has to be able to look at, at that sum array. Okay? So that's shared. So that's good. Okay, so, C and D were the winners. So for you guys, so far we're doing well. Now here's where you guys and I have a little bit of a difference. So I believe that half has to be private. And most of you guys believe that it had to be shared. Or at least that it could be shared, okay? And here's the problem, and this is fundamental. This is why I love this clicker question, even though I made it up. So I guess I'm allowed to love it. Here's your problem right here, right? You've got in that first round, you've got 100 processors executing that instruction, okay? If half was a shared variable, it'd be gone, right? You'd be done in that first round. Okay, so the only way this thing's going to work is if everybody simultaneously does that same calculation. So this gets to the earlier question, which is, boy, it seems really wasteful to have, everybody doing the same calculation over and over again. But that's the only way this code's going to work. Okay, so in this case, I'd like to say that thank you to the 18% who agreed with me. Does anyone in the 63% want to argue with me and the other 18%? And I'll let you argue with them, not me. Okay, so let's keep going. But if you understand this, you understand a lot about how this processing is working. Okay, So we talked about coordination a little bit. Oh, well, we talked about how information is shared, okay, through memory and through these variables, right? Sum was a shared variable that everyone got to look at, and that's why this thing worked. But now let's talk about how things work with multiple processors. Okay, and the issue is that, we already had a problem that memory was really slow, right? So when we start adding more and more cores, that problem is only going to get worse, because now instead of having one CPU that's going after the memory, you've got multiple. Okay, so memory is going to become even a worse bottleneck. So you're going to have to do caching. Okay, so caching was important when we had a single core. It's even more important when we have multiple cores. Okay, so now we've got a real problem, though, because if you remember, we had this in our architecture. Do I have a picture? Yes, thank you. Each processor has its own cache. So what's going to happen? So look at the problem. This is another animation. I credit the guys who taught it last year for this animation. So let's say you've got three processors. I don't know why there's a gap here, but okay, three processors. And let's say processor 1 and processor 2 want to read the value at memory location 1000. So processor 1 says, hey, go load the value at 1000. That goes in the cache. That's a cache miss. So then I go out on the interconnect, I go out to the library or to Sacramento or wherever that was, pull the thing back from it, look in memory, oh, it's 20. That comes back through the interconnection network, and then I cache it. Okay? So that's one. Then processor 2 says, hey, I want to read location 1000. Why would they ever do that? Well, we just showed you there's a bunch of shared variables, right? So it's actually very likely that another processor is going to want to read the same location. So it says, okay, I want what's at location 1000. Same thing, goes faster because I don't want to animate it all through the cache. The answer is still 20, so that goes back and stays in that cache. Okay? So now processor 1 is happy. It's got the value local. It can run really fast. Processor 2 is happy. It's got the value. It can go really fast. Now, all of a sudden, the processor 0 decides it's going to update location 1000. Okay? Well, what happens there? Well, processor 0 says, okay, is 1000 in my cache? I'm going to write it. Well, it's not in the cache. It's going to go out in the interconnection network. And now something really interesting happens. Okay? If processor 0 were to go ahead and just update location 1000, right? If it's just doing a store, so it actually didn't even have to read it, right? It could just do a blind write into the cache. But why is it going out to the interconnection network? Well, the problem is if processor 0 updated its local copy, processors 1 and 2 would have the wrong value, okay? Because this is supposed to be a shared variable. If any processor accesses a particular location, if it's shared, everybody should see the same value. And if processor 0 just went ahead and did an update, the other guys would have an out-of-date copy. So we've got to do something about that. This is called cache consistency, or cache coherence sometimes. So what we're going to do is we're going to say, okay, when processor 0 wants to do that right, when it goes to the interconnection network, the logic, the hardware actually, the caching logic, is going to say, okay, well, I better clear 1000 out of those other caches. And so it does what's called an invalidation, and it removes 1000 from those caches. Okay? Once it does that, processor 0 is free to update location 100. In this case, 1000, it writes 40 into it, and the system's still consistent. Nobody's seen any bad data. Let me show you another slide or two before you ask questions, and then we'll see if you still have the questions. Okay. Okay, and if you're doing write through or write back, eventually that thing's got to go back to memory, right? Okay, so let's look at it. Maybe that's all I had in that example. Okay, so there's going to be a protocol to make this work. I'm going to tell you about it. So let's get a couple of questions. Yeah. What if the piece of data was in the register? Okay, that's an interesting question. So is there a race? So what you're talking about is something called a race condition, and we're going to talk about that in a second. So there's some issues you got to keep track of to make this work. Okay, let's see. I'm just going to go in this direction. Yeah, go ahead.
So by clearing and changing the value of processor 0's cache, we just took it out of the cache of processor 1 and 2.
Right.
Oh, okay.
That's called an invalidation. That's what we did to make everything work correctly. So yeah, so when processor 0 goes to do a write, that invalidates the entry in processor 1 and processor 2. And by the way, remember we had that valid bit in the cache? Remember that extra bit you always had to worry about to get your exam questions to work out right? So we don't actually take the thing out of the cache. We just flip that valid bit to invalid. That's called an invalidation. So it's no longer in the cache. Okay, yeah.
Considering that we're getting more and more processes all the time, would it make sense to kind of have like an L3 cache that works up for all the processes with only hold shared variables? You could have like a new one or two new instructions to store a shared variable as opposed to back.
Okay, so the question is that, as we're getting more and more processors, we're going to have more and more conflicts like this. So maybe a better thing to do is to have a bigger shared cache. And that's true, except remember, any shared cache, just because of the way these things are going to be laid out on the chip and the coordination logic, is going to be slower than the local cache. So you really want to have a good-sized local cache so that things go fast enough in the normal case. I think I skipped you already, so let's go. I'll come back. Yeah. Why doesn't it just overwrite the other cache? Okay, so I'm not. So the question is, why does it invalidate these caches? What else could you do? You could send the new value back to them, for example. You could totally do that, and believe it or not, I actually wrote my PhD thesis on algorithms to do exactly that in a distributed system. So I'm showing you sort of the simplest, most basic way of doing it. There's tons and tons of ways of doing this. Yeah, let's go back here a little bit. Yeah.
If you're using write back cache,
Yep.
it's still in the cache of processor 0, but another processor requests the data.
I'll show you how that works in a second. So if, I showed this as kind of right through so that memory was kept in sync with the caches, but it doesn't have to be that way. Remember, we had this thing called a write back cache. Very good question. And I'll show you how that works in a second. Yeah. Yep. Yep. Oh, was that the question? Okay. Okay, so I think the question is, okay, so we said that L1 and L2 were local to a core. They were private to the core. And then L3 was shared. And yeah, this picture isn't showing an L3. Okay, so there's no L3, there's no shared cache in here. There's just memory. There's just level 1, level 2, and memory. Okay, yeah, in the back there. Yeah.
Why can't processor 2 check processor 1 cache or memory?
Why can't it check it for what?
For the memory, instead of having to go all the way out for memory.
Oh, okay, great. So you guys, as usual, so the question is, why does processor 2 have to go all the way out to this slow memory to get something? Why couldn't it just get it from this fast cache on processor 0? And yeah, or at least check it. And that's a brilliant idea. That's what's called snooping, or sometimes Snoopy caches. I'm going to show you how that works in a second. So we are actually going to get a bunch of sharing of some sort across these caches. But you got to remember, the whole thing, right? Remember, level 1 cache has to go really, really fast, right? It has to be no longer than a clock cycle. Okay, and level 2 cache has to be pretty fast. So you don't have a lot of, you're not running a big program to do this, right? This is all happening in logic. And it's got to go fast, and it's got to be simple. All right, one more question. Yeah?
If we were using these 3 processes to do the second task,
Yep.
and we had the shared variable, wouldn't it make sense that once one of them loads it, they all load it?
Okay, so the question is, if we knew this was a shared variable, which the hardware might not know, but we might be able to tell it, maybe it would make sense to, when one of them updates it, to broadcast it to everybody else. Yeah, I mean, there are definitely protocols that work that way too. Okay, and so it's kind of a trade-off between, the cost of. I mean, think about doing that. Think about sending that to a cache that's not ready for it, and how that logic's going to have to work. It makes things complicated. All right, I really want to move on because it's getting a little late. Let's look at a little more of this, and then see if that answers the questions. Okay, so how are we going to make this work really? Well, we're going to. The basic idea is, I think you guys have already figured out, is that if a bunch of processes or a bunch of threads are reading something, that's great. Everybody can have a copy in their cache. That's not a problem. The thing is that if somebody writes something, that's when you get this consistency problem, right? If nobody's updating it, you can make as many copies as you want. As soon as one thread tries to update it, then you've got a consistency problem. So we solve that in this scheme through invalidation. As you guys have already figured out, you could also, instead of doing invalidation, you could broadcast the new. There's a bunch of things you could do. Invalidation turns out to be the thing that most systems implement. Okay, and yeah, there's another problem, which is, if processor 0 is writing it and processor 2 is writing it, this thing's going to ping-pong back and forth. And, to fix that, you have to sort of rewrite your program. Okay? All right, so how's this going to work? So you already sort of understand the basic mechanism, which is we have in the cache, we have, in addition to the data and the tag bits, we have some other bits that we use to tell us what's going on. And what we've seen so far is we've seen the valid bit, right, which says if it's 1, then the thing that the tag represents is actually in the cache. And if it's 0, that means the thing that's in the cache is garbage. Don't look at it. Okay, and we have this thing called the dirty bit, which says, hey, this thing has been updated, but it hasn't been written back to memory yet. Okay? So what we're going to do is we're going to add some more bits so that we can have more states, right, so that we can have more information about each of those cache blocks. Okay, so we're going to come up with we're going to come up with a bunch of new states. So a cache block now, in addition to just being invalid or valid or dirty or not dirty, it might be marked as shared. Okay? So let me just show you the options, and then we'll talk through them. Shared, modified, and then invalid. Okay, so invalid we already know. Means the thing that's there is garbage. Don't look at it. Shared says if you get a cache hit, and you look at the bits in the cache, and they tell you the status bits, they tell you that that block is shared. What that's telling you is that that data you're looking at is up to date. Okay, so that's cool. You're not allowed to write it unless you change its state. Okay, so if you want to write this thing, you've got to do something else. You can't just write it because other caches might have a copy. Okay, and then also, by the way, the copy that's in memory is up to date. So that's a good thing. All right. Another status you might have is something called modified, which says, okay, if you've got the version, if in your cache this block, the data of that block is marked as modified, then that means what you're looking at is up to date. It means it's dirty, which means it hasn't been written back to memory. So the thing that's in memory is out of date, and you can write it, but and furthermore, because we do this invalidation, we know that no other cache has a copy of it. Okay? So what that means is if somebody else wants to read this thing, they can't read it from memory because what's in memory is out of date, right? Oh, where are we? Copy in memory is out of date. So that means you have to be listening on that interconnection bus, and if a request comes in for a block that you have modified, then you have to be the one that serves it up to them, okay? Because they can't get it from memory. So typically what you'll do is you'll change its state in your cache to something like shared, write it out to memory and also give it back to the processor that requested it. Okay, so that's shared and modified and invalid. There's two others, and you can make a perfectly good protocol just with those three states. And in fact, the thing I showed you on that first slide only use those states. Okay, but systems that have been implemented also typically have a couple other states in order to make things run faster, just like you guys were doing. The designer said, well, here's this common case that's going to happen a lot. Maybe we should do this other thing that's smarter. Well, the way you do that, the way you tell the cache how to do that is you invent a new state, and you build the cache to be able to do the right thing for that state. So another state that is out there is exclusive, okay, which means you've got the up-to-date data. It's okay for you to write it, but when you write it, you've got to change its state to modified. No one else has a copy. That's what exclusive means. And exclusive also means that the copy in memory is up to date. Okay? So if you want to write it, you change it to modified. What that means is that the copy that's in memory is no longer up to date, or it won't be after you do the write. Okay? So if you're the exclusive owner, you also have the option of responding to read requests. Owner is a slightly different one than exclusive. Basically, it says you have the up-to-date data. It's okay for you to write it as long as the difference between exclusive and owner is exclusive, you know that no one else has a copy. Okay? Whereas if you're the owner, other caches might have a copy of it. Okay? Now, those copies have to be marked, if they have them, they have to be marked as shared. And so if you want to do a write, you have to do what we showed you in that slide, which is you have to go out, invalidate those copies in those other caches, then change your state to modify and so on. Okay? So, so what's happening here is we've got these different states that tell the caching system facts about the world, right, invariants. So if I've got a copy of a piece of data in my cache and it's marked exclusive, I know these things to be true. I know no other cache has a copy, okay? And I know that the copy that's in memory is up to date, so I don't have to worry about writing it back if I decide to drop it, okay? There's a bunch of things like that. And each of these states tells you a bunch of facts about the world, and you can use those facts to do the kinds of optimizations that you guys were all talking about, to avoid having to go to memory too much, to avoid having to write things too much, and to avoid having to invalidate copies of things when you don't really need to for correctness. Okay? So this is sometimes called the Mosey protocol. And again, it's what's called a snooping cache protocol, or a Snoopy cache protocol. And what that means is the caches listen to that traffic on that interconnection bus, and sometimes they answer instead of the memory. Okay? If you're the owner and somebody asks for something, you're the one that has to answer. Okay? Or I'm sorry, if you have it exclusively, for example. All right, or you have it modified. So now the question is, how do you describe these things? And this is what's called a compatibility matrix. And what this says is, if I've got two caches, okay, and let's say this is cache 1 and this is cache 2. If cache 1 has a piece of data, has a data item or a block in modified state, then what can the other processor have it in? And basically, it's not allowed to have it modified, because only one processor can have it modified. It's not allowed to have it shared, right, because the rule for modified is no one else has it. And it might be invalid. That's fine. It can be in another cache and marked as invalid. Okay, for shared, no one else can have it marked as modified, but other caches can have it marked as shared. Okay, and invalidate, yeah, sure, they can be invalid all over the place. That's not going to matter. Okay, so that was the first one I showed you, right, the modified, shared, invalid. If you add these two extra ones, they don't make anything more correct. MSI is going to be correct if you do it, if it's implemented the right way. But you can make it more efficient by adding these other states. And these other states look like this. It's kind of interesting. What gets added is that you can have one cache that has it marked as shared while another one has it marked as the owner. Okay? And that's basically what adding these new states adds to this compatibility matrix. Okay? And if you take all this together and you take those definitions that we just talked about together, the way that ends up looking is through this kind of a state diagram where you basically have your 5 states that a cache block can be in. So, for example, if you've got it marked as shared and then you get a local read hit, then it stays shared. If somebody else asks for it, all right, you can give it to them and it still stays marked as shared for you. Okay? If you've got it marked as modified, then, if someone else tries to read it, then you can give it to them, and then you have to move your state to owned. Okay? And so if you look at this state diagram, that tells you how these things are all related. And this is one that comes from an AMD processor. I just grabbed the whole slide from their website. I'm not sure. The MIPS implementation of this might have a few different arrows in a few different places. So just to warn you. But this is one example of a cache coherence protocol and how all the pieces fit together. Okay, and if you look on Wikipedia, for example, there's a pretty nice web page, I used it, that explains these things. And you'll see that there's a bunch of different variants of this Mosey protocol. And all the variants come from exactly what you guys were just doing, saying, hey, here's a case that I think is important. I want to add something to the protocol to make that happen normally. All right? Okay, so one other thing about cache coherency that I want to mention is there's a fundamental problem with this kind of caching that we're doing, because you might end up with what's called a false conflict. So let's say your cache block is 32 bytes, okay? And let's say I've got some processor 0 that's reading and writing some variable x, and I got processor 1 that's reading and writing some other variable, processor y. These things have nothing to do with each other. There's no reason there should be any conflict here. Okay? But what's the potential problem? Let's say x and y are 4-byte integers. When could I get into trouble here? Or not in trouble, but when could something inefficient happen? It won't be incorrect, but it'll be inefficient. Yeah. Yeah, when x and y are near each other in memory, and worse than that, they're so close that they're in the same cache block, right? Because 32 bytes, right, that means you can have 8 integers in there. X and y are integers, they might very well end up in the same cache block, especially if you're being very careful about laying out your memory with, in the smallest possible place. And so, for example, let's say x was in 4000 and y was in 4012, then, when x goes and updates, when 0 updates x, that's going to invalidate y's copy of that cache block, which means y is going to lose, 1 is going to lose its copy of variable y. It's going to have to go get it again. Okay? So this is what's called false sharing, and, it can cause caches to be unnecessarily inefficient. You can get more misses than you should get, and as you know, misses are very expensive because we're trying to keep that cache hit rate high so that we can keep our processor going at full speed. If we get a cache miss, we have to stall the processor, wait for that miss to be resolved. Okay? So what might you do? How might you fix this problem? Anyone have any ideas of how to fix this? Yeah? Yeah, so you'd separate the variables in memory so that this doesn't happen. Who would do that? Okay, well, see, you shrugged. You're not allowed to shrug. Who would do that is either you, if you're writing in assembly language, or hopefully the compiler, right? The magical compiler. This is the kind of thing that compiler writers have to worry about. So the compiler can look at the code, can see these kinds of problems, and can do the layout to avoid them. In some cases it's hard to tell. Okay, so this is just some things that you need to think about. So you as a programmer can be smart about where you put things, maybe spread them out a little more than you might otherwise, and the compiler can be smart, probably smarter than you because it looks at all the code. Yeah. So I don't have a hardware fix for this. I'm suggesting, smarter code, either written by the programmer or more likely by the compiler, generated by the compiler. Yeah. Okay. So all that's happening here is happening because we have, as we discussed last time, multiple threads of execution, right? So we have not just a single path through a program, but we have a bunch of code and we have multiple execution paths that are happening at the same time. And on a single processor, they might happen in the same time because you're swapping them out, right? That's called time division multiplexing or kind of time sharing, okay? And then you switch from one thread to another. But for sure, it's going to happen on a multiprocessor. And as we said, basically all CPUs or all chips you get these days are pretty much multiprocessors. So this is going to be a problem that's hard to avoid. I'm going to have to keep going because I want to get through a couple things. So, okay, so good. So let's see if we can figure out, let's see, let me figure out how I'm going to do this. Okay, so you can, so the question was sort of how do we know how many threads there are, how many processors there are. So if you look, if you have a Mac, there's a command called syscontrol, and I think it's in Linux. I know it's in BSD. You could try it. If you try it, be really careful because if you use the wrong flag, it actually changes the values. So don't use any flags. But what it does is it tells you cool stuff about what's going on your machine. So, that's not going to be cool. Okay, so for example, and I hope this isn't too much of an eye chart, it tells me I've got 2 CPUs. That's kind of interesting. It tells me my byte order is 1, 2, 3, 4. What's that? Big Endian, Endian, Little Endian? Little Endian, yeah. Dan knew. That's Little Endian. So I just found out my processor's Little Endian. That's good. I've got 2 physical CPUs, okay? So I've got 2 cores. I've got 2 logical CPUs. That means there's this thing called hyperthreading, which is kind of a cheating way of adding a sort of a partial core. So we're not doing that stuff, okay? And Oh, this is too bad this is split. This is telling me something about my cache configuration. This is kind of cool. This is telling me I've got 3 levels of cache, okay? But it's actually not true. It's basically saying this is memory, this is level 1, this is level 2. And this number is telling me, to get to the question that was asked earlier about sharing, this number is telling me how many cores get to look at that level of the memory hierarchy. So this is telling me I've got 2 cores that can access the memory. Each level 1 cache is private to a core. The level 2 cache is shared by the 2 cores. And I bought a cheap machine. I don't have a level 3 cache. That's what this is telling me. And then you can look, and it'll tell you things about the cache sizes. So a cache line is another way of saying cache block. So on this machine, the cache block is 64 bytes of data. I've got 32K of them in my iCache level 1. I've got 32K of them in my data cache on level 1. And the level 2 cache size is 3 million of those guys. Okay, so it's a pretty big, I'm sorry, this is bytes. So you got to divide this number by 64 to get the number of cache blocks, sorry. So I've got a 32K iCache, a 32K Dcache. I've got a 3 megabyte level 2 cache that's shared by my 2 cores. Okay? And if you run this on your machine, you'll see different numbers because you might have bought your machine, after I bought mine, and so it's got more stuff, or maybe you paid a little less and it's got less stuff. Okay? And then if you just go through this, there's just all sorts of great stuff. Let's see, what else did I want to show you? Oh, this is kind of fun. Remember we studied the SSE instruction set? Well, this tells me which ones of those my processor supports, and it seems to support the original 2, 3, and the first version of 4, but not the second version. So that's kind of useful, too. And then there's a bunch of other stuff in here. So that's one way to find out some stuff. The other way to find out some stuff about your machine, at least if it's a Mac, is you go to About This Mac, you go to More Info, and that's going to tell you some fun things like, a little more readable, like I've got an Intel Core Duo, what the clock speed is, how many cores, how much cache I have, how much memory, and stuff like that. So, the question about how does the compiler or whatever piece of software know how many cores I have, what the cache size is and all that, there's system calls to find that stuff out, okay? All right, so we're out of time. What we're going to talk about next time is the last one of thread level parallelism. Have a good weekend. Good luck on your projects.